Hi, thank you for your interest in our paper, DUET, Boosting Deep Neural Network Efficiency on Dual Module Architecture. I am Liu from UC Santa Barbara. As we know, DNNs have been widely used in recent years and are driving many applications, whether it's vision, speech, NLP, autonomous driving, and or like medication such as drug discovery. However, deploying DNNs are very challenging to meet the latency requirement or the energy constraints. On the one hand, the feed-forward networks and the recurrent neural networks showing low operational intensity and thus are very memory bounded. On the other hand, we also need to deal with highly compute-intensive models like CNNs. So we believe that general machine learning acceleration should cover both ends of the diagram. Why we used to treat DNN acceleration as data manipulation, like matrix or matrix vector multiplication. Computing activations is at the core of DNN processing. In fact, DNNs are powerful because of the ability to model complex nonlinear relationships. So we're not really dealing with simply a matrix multiplication. It is more like activated matrix multiply. And the use of nonlinear activation function is what enables neural networks to be deep. Given this point of view, that all the expensive computations and data access of DNN processing all ended up with computing for activations. And here comes the question, do we really need to compute all activations accurately? Our answer in this work is not really. We observe noise resilience in DNNs because of using nonlinear activation functions. Essentially, nonlinear activations have these particular regions that if we add noises to the input, the output activations are not affected. We refer these regions as insensitive regions, and these activations being insensitive, we show three common activation functions in DNNs. The shaded green area is insensitive, and the dark green means more insensitive. As you can see, the most straightforward case is value. The pre-activated value doesn't matter as long as it stays negative, and the output activation is zero and not affected. Other complex activation functions like hyperbolic tangent and sigmoid have similar insensitive regions at two sides. To summarize, DNN activation functions are noise resilient, and one key implication is that these insensitive activations can afford approximate results. To get a sense of how much percent of activation is insensitive, we provide activations of pre-trained CNN and LSTM models, and we found out that a large portion of activations are actually insensitive. So far, we have looked at the noise resilience in DNNs, but how can we leverage this kind of noise resilient feature to reduce memory access and computations? What we propose here is dual module processing. The intuition follows closely with what we observed. Since the insensitive activation can afford some sort of noises, why don't we use a very light-weighted approximate module to compute for this insensitive result? And we only need accurate computation for the sensitive activation. So given a layer from a pre-trained model, we refer it as the accurate module. And we learn the approximate module from the original layer. And at inference time, we pay very little overhead of the load and compute of the approximate modules, but we can save expensive compute and memory load of the accurate module. Another important feature we want to mention is that the selection of sensitive or insensitive activations is dynamic and input dependent. As you can see in the figure, the activation maps are from the same layer, but given different inputs. We can see that the selected sensitive activations, that's those dark dots, are dynamic and input dependent. So why model compression techniques like weight pruning and model arc optimization have been used to reduce redundant computations? We regard them as static redundancy. we look at dynamic redundancy in activations. As you can see, our approach is orthogonal to model compression, and we have also applied on proved models. With that, let's talk about how to get approximate modules. We need to achieve twofold design goal. First, the approximate module have to be lightweight and with much fewer computations and memory accesses. Secondly, the approximate modules need to approximate the original modules accurately to preserve the model quality. We adopt a learning-based optimization method to train the approximate modules. First, given a pre-trained layer, we freeze its parameters. Then we construct the weight matrix of the approximate module to have smaller input dimensions. And a key step is performing dimension reduction step on the inputs to match the weight matrix. And we choose ternary random projection as the dimension reduction method due to its good distance preserving and hardware-friendly implementation. After that, we compute the mean square error of the results from both approximate and accurate modules, and then backpropagate gradients to adjust the approximate module's weight. After convergence, we use dynamic switching at inference time. Let me explain it with more details. First, we execute the approximate module to get the result. Then, we generate the switching map based on thresholding. And a 1 in the switching map means the activation value is sensitive, and we need the accurate result for that. And vice versa, the 0 means the activation can have approximate results. So with the switching map, we can then load and compute the corresponding output activations. And a special case of matrix vector multiplication, as in FFNs and RNs, is that we can directly save memory loading of those weight vectors, contributing to the insensitive activations. Finally, the resultant activation of this layer is a mixture from both modules. So why the dual module processing method can save computations and data access theoretically, it also brings challenges to the hardware accelerator design. Specifically, we need to have an efficient design for running approximate modules. And then dynamic switching can save computations, but also introduce irregularities. So the local control of PE needs to handle that. Finally, any computation skipping would cause imbalanced execution, and our proposed adaptive mapping strategy comes for remedy. Before we look at these countermeasures, let's first go over the high-level design, the dual module architecture. Intuitively, we have an executor to run accurate modules and a speculator to run approximate modules while sharing the same global buffer. We choose a decoupled design. That is to say, we let the executor and the speculator to run in parallel. So the latency of the speculator can be hidden with fine-grained pipeline. And we also need the speculator design to be area and energy efficient. Then let's have a look. Let's have a quick look on the design considerations. So first, we can use much lower precision in the speculator. Again, because of the noise resilience we have seen. In our design, the speculator uses fixed point 4-bit, while the executor uses fixed point 16-bit. Then, because of the two computation steps in running approximate modules are very compact and dense, so we can use very efficient adder tree with alignment unit and using a systolic array to finish the computation in approximate modules. And for the executor, we adopt the spatial 2DP array architecture due to the energy efficiency of local data reuse on the 2-level on-chip memory hierarchy. And then the PE will load dynamic switching maps from global buffer, and the local control logic handles computation skipping from dynamic switching. orchestrating and executing multiple MAC operations. As you can see in this example, applying a 3x3 comp kernel on a 5x5 input results in a 3x3 output with 81 MACs in total. Each MAC operation can be viewed as a micro instruction, where it has indexes for output activation, wait, and input activation. Here we use a lookup table to store these micro instructions. And enabled with dynamic switching. Here in this example, we show both output and input switching. As you can see, after skipping unnecessary micro instructions, now we only need 13 MACs versus 81 MACs as in the base case. What's not shown here is that we use priority encoder to select valid micro instructions from the lookup table. And you can have more details in the paper. Finally, let's look at the imbalanced execution problem. For example, we're mapping 4 channels of output activations on 2 rows of PE in 2 steps. The naive mapping chooses output channels sequentially, regardless of the workloads of each output channel. So this mapping causes idleness of PE and thus compromises the performance. Enabled with adaptive mapping, channels with similar amount of workloads can be mapped on the same step, causing less idleness. And please note that our mapping strategy doesn't increase burden on buffer accessing, and it will also keep the energy efficiency. With that, let's go over some key evaluation metrics. First, we will see the trade-off between quality and saving, and then we will show the performance improvement and energy efficiency. Last, we will give the overhead analysis of dual module architecture. Here, we show the key result of Resident 18 and GMT on image classification and machine translation, respectively. As you can see in the table, within 1% top point accuracy job, our method can achieve 5 times flops reduction. And when limiting the accuracy job to 0.5%, we can still achieve 4.7x reduction. And on GMT, we can have 2.2x data access reduction with unnoticeable translation quality degradation. With the same level of operation reduction and data access reduction over a benchmark of CNs and RNs, our design can achieve on average 2x speed up and energy saving compared with baseline cases. And the overhead of the speculator running approximate modules is a major concern. As you can see in the figure, the gray bars are the base case without speculator. The blue bars and the green bars represent the executor and the speculator in dual module architecture design. So the DUET latency, that is the largest among dual module, is significantly less than the base case. And in most situations, the latency of speculator is less than the executor. Our design choice of the speculator takes 6.6 total chip area. And of course, larger speculator would further reduce latency, but contribute little on the final performance. Energy-wise speaking, speculator consumes 3.5 to 6.3% on-chip energy for those count layers, and they consume less than 1% for RNs. To summarize, we propose a co-design that leverages the noise resilience in DNNs to exploit dynamic activation redundancy elimination. With the dual module processing method, we specialize the accelerator architecture with decoupled executor and the speculator design. The overhead of the speculator is small, and we propose adaptive mapping to achieve balanced execution. Thank you for watching. Our paper is on session 4, Machine Learning Accelerators 1, and looking forward to meeting you and addressing the questions.